Just a few decades ago, these spinning devices were a common sight atop industrial facilities, storage buildings, agricultural structures, and even homes throughout the United States and Australia. However, if you explore any contemporary residential development in the country today, you'd be hard-pressed to find even one. These are known as turbine ventilators or whirlybirds. Independent evaluations have demonstrated their ability to lower peak attic temperatures by as much as 37 degrees Fahrenheit and reduce cooling expenses by approximately 15%, all without consuming any electricity or employing any electronic components. But if they were so beneficial, why did their use decline? And if their efficiency is as high as the test results suggest, should we reintroduce them? Let's investigate. The concept of moving air through a structure without relying on combustion or energy consumption represents one of humanity's most ancient engineering solutions. We've previously examined this mechanism. Persian builders utilized such systems on multiple occasions, as discussed on this channel. Tall stone wind towers, referred to as badgers, were ingeniously designed to direct desert breezes downwards into the lower levels of a building, while simultaneously drawing out the hot, stagnant air from the upper sections. Yet they weren't the sole practitioners of employing air currents for interior climate control. During the Tang Dynasty, Buddhist monks incorporated natural ventilation channels throughout their cave complexes to regulate temperature and air quality within these subterranean environments. Furthermore, by the Middle Ages in Europe, air was considered one of the four fundamental elements, and the manner in which a building exchanged air was deemed as critical as the respiratory health of its occupants. These were all examples of passive systems, deriving their functionality from the building's design and prevailing winds. The impetus towards more active solutions emerged during the Industrial Revolution. The demanding conditions in deep mines necessitated methods to sustain workers underground, prompting engineers to develop fire-driven ventilation systems and manually operated wooden fans. By the 18th century, the Houses of Parliament in London had implemented a rudimentary mechanical system, known as a blowing wheel, intended to replace stale air with fresh. And by the 19th century, figures like David Boswell Reed were constructing steam-powered ventilation systems for hospitals and barracks, where the danger of airborne contagions rendered air movement a matter of life and death. However, all these systems demanded fuel, supporting infrastructure, and ongoing maintenance. The significant advancement occurred in 1910 when an engineer named Samuel Ewart patented a design for a rotating cowl intended for roof installation, which actively drew air from the space beneath it. Ewart's original patent described the invention as a solution for both ventilation and for preventing downdrafts in chimneys, those sudden gusts of wind that would force smoke back into a dwelling. Crucially, unlike any preceding design, his device required no fuel source, no electricity, and no human intervention whatsoever. Ewart's innovation was elegantly simple yet profoundly ingenious, capitalizing on three distinct principles that work in concert to resolve a common issue faced by virtually every residence. During a typical American summer, solar radiation heats the roof's surface, transforming the attic into a reservoir of heat. Temperatures within this confined space can surge beyond 150 degrees Fahrenheit, and this accumulated heat does not remain static. It radiates downwards through the ceiling and into the living areas below, compelling your air conditioning system to operate for extended periods, exert more effort, and consume additional electricity simply to maintain a consistent interior temperature. According to the United States Department of Energy, each degree Fahrenheit increase in attic temperature can escalate your cooling demand by up to 4%. Moreover, in numerous homes, the air ducts responsible for distributing cooled air traverse directly through this intensely heated attic space, meaning the air warms up again before it even reaches the intended rooms. Therefore, the primary objective of attic ventilation is to disrupt this cycle by expelling hot air before it has the opportunity to radiate downwards. This is precisely the function for which Ewart's turbine was conceived, utilizing three synergistic principles. The first is Bernoulli's principle. As wind flows over the curved blades of the turbine's head, the air is compelled to accelerate. When air velocity increases, its pressure diminishes. This generates an area of low pressure within the turbine, creating a suction effect that actively draws warm air upwards from the attic and exhausts it externally. The critical distinction here is that, unlike a static vent that merely allows air to drift out passively, the turbine ventilator harnesses the wind's kinetic energy to actively pull air from the building. The greater the wind speed, the more effectively the turbine operates. However, a widely overlooked aspect is that the turbine's operation does not cease when the wind subsides. It also utilizes what is known as the stack effect, which is the inherent tendency of warm air to ascend. Warm air possesses lower density than cool air. Consequently, in a building equipped with soffit vents at the eaves and a turbine at the roof ridge, this rising warm air generates a gentle pressure differential that propels air upwards and out through the turbine, even when it is not actively spinning. The third principle at play is the Venturi effect. As air is constricted through the narrow channels between the rotating blades, its speed increases, further reducing the pressure within the turbine housing and accelerating the expulsion of air. All three of these phenomena work together synergistically. The outcome is a device that consistently generates negative pressure at the building's apex, drawing out hot, humid, and stale air, and replacing it with cooler air admitted through the soffits below. This straightforward design has proven to be exceptionally effective. A study conducted by the Air Infiltration and Ventilation Center revealed that the installation of a turbine ventilator resulted in an average annual increase in attic ventilation rates of 15%, with improvements reaching up to 50% when the wind struck the unit from its optimal angle. Data gathered in the San Diego region indicated that a correctly installed turbine system reduced peak attic temperatures by as much as 37 degrees Fahrenheit, translating into an average reduction in energy bills of 14.6%. To illustrate this in practical terms, a standard 12-inch turbine can move between 250 and 350 cubic feet of air per minute with a mere 5-mile-per-hour wind. A 14-inch unit increases this capacity to between 350 and 500 cubic feet per minute. And since the device consumes no electricity, every dollar saved on cooling represents a direct financial benefit. However, these figures are accompanied by a significant caveat, contributing to the diminishing prevalence of turbine ventilators in the United States and globally. A study from Deakin University found that while a single 12-inch turbine could achieve an airflow rate of approximately 150 cubic feet per minute, the resulting air velocity within the roof space was only about 1/3 of a foot per second. In ventilation terminology, this is technically classified as stagnant air. Their conclusion was that a single turbine is often insufficient to handle the thermal loads of a modern residence. This is precisely where appropriate sizing becomes paramount. Most building codes recommend 1 square foot of ventilation for every 300 square feet of attic floor area. However, in regions with hot, humid climates such as Florida or Texas, many professionals advise doubling this ratio. Yet, the performance limitations of a single unit represent only one facet of the issue. The most problematic aspect was mechanical failure. The defining characteristic of the turbine, its rotating head, is also its primary point of vulnerability. Over time, the ball bearings can deteriorate due to moisture, dust, or inadequate lubrication, leading to a squeaking or grinding noise that transmits through the roof structure and into the living space below. Inexpensive, poorly manufactured units are particularly susceptible to this, which over the years has contributed to the turbine's reputation as noisy and unreliable hardware. Furthermore, there is a more subtle engineering challenge known as short-circuiting. This occurs when a turbine and a ridge vent are installed on the same roof above a shared attic space. Because the turbine draws air more forcefully, the ridge vent can inadvertently reverse its function and begin pulling outside air in, consequently admitting rain and snow instead of effectively exhausting warm air. For this reason, most roofing professionals recommend selecting a single exhaust system and adhering to it. And since ridge vents are generally simpler to install, the turbine is typically the component that is omitted. Beyond the engineering considerations, there is the matter of aesthetics. Turbine ventilators are highly visible from the street, and in the American housing market, Curb appeal significantly influences property value. Ridge vents, by contrast, are designed to be covered by shingles, rendering them virtually invisible from ground level. Homeowners associations across the nation have frequently imposed restrictions or outright prohibitions on turbine ventilators because they detract from the clean, uniform roof lines characteristic of modern suburban developments. Even in Florida, where state law protects energy-saving devices, many homeowners associations have found ways to circumvent this by mandating that turbines be positioned solely on the rear slope of the roof, which may not align with the prevailing wind direction, thereby diminishing their effectiveness entirely. Building codes have also complicated the implementation of turbine ventilation. As American homes have become more tightly sealed and energy efficient, regulations such as the International Energy Conservation Code and California's Title 24 have begun to mandate mechanical ventilation systems capable of ensuring precise air exchange rates. Because a passive turbine's performance is contingent upon wind speed and ambient temperature, variables beyond human control, it falls into a regulatory ambiguity. Therefore, the pertinent question we should now address is whether we should universally adopt the turbine ventilation system. The honest answer is entirely dependent on your geographic location and your specific objectives. If you reside in a region characterized by a hot, windy climate, such as the Gulf Coast, the American Southwest, or substantial portions of the Sun Belt, a turbine ventilator remains one of the most economically viable methods for reducing your cooling load. The material cost for a single 12-inch unit ranges from $20 to $100. Professional installation adds an additional $100 to $300 per unit, contingent upon factors such as roof pitch and installation complexity. For a typical 1,500 square foot attic, 2 units are generally considered adequate. In a southern climate, the energy savings realized can recoup the installation costs within 3 to 5 years. Moreover, because proper attic ventilation prevents shingles from overheating and the roof deck from retaining moisture, the device can extend the lifespan of your roof by several years. However, in colder climates or in homes featuring modern, high-performance building envelopes, a turbine is likely an unsuitable choice. During winter, internal moisture can freeze the rotating blades solid, rendering the system inoperable at precisely the most disadvantageous time. And in an airtight home where mechanical ventilation already manages air exchange, introducing a passive exhaust point can disrupt the pressure balance that the system was engineered to maintain. Realistically, for the majority of homeowners, particularly those undertaking new construction or roof replacement, a ridge vent is likely the more practical option. A full-length ridge vent extending along the entire span of a standard roof provides over 900 square inches of unobstructed ventilation area, roughly double the capacity of 3 14-inch turbines. And because the ventilation is distributed uniformly along the entire ridge, rather than concentrated at 2 or 3 isolated points, it effectively eliminates the dead zones that turbines can create in attic corners. Ridge vents possess no moving parts, no bearings prone to failure, and consequently no noise complaints or correspondence from homeowners associations. They simply remain in place and function effectively year after year. If you found this video informative and appreciate learning about methods to enhance self-sufficiency and energy independence, then subscribing and sharing it is the most straightforward way to ensure such valuable knowledge continues to be discovered. And if you are interested in understanding how the principles of thermal buoyancy can be applied to cool an entire residence without any electricity whatsoever, then you should definitely watch our video on solar chimneys, which is available right here.